In this video, I'm going to talk about the strain-displacement matrix, also known as the B matrix for a bar element. In the previous video, I derived the equation for stiffness matrix for a bar element, and we had a quantity which I said I will discuss in the next video, which is the B matrix, also known as the strain-displacement matrix. So, the finite element works in a way that when you have two nodes in an element like this, you can obtain displacement at these nodes by using the equation P is equals to Ku, where K is the stiffness of the element and U are the nodal displacement. So if we have vector of two forces such as P1 and P2 applied at node 1 and 2, so we have P1 here and P2 there, then we will expect displacement U2 at node 2 and U1 at node 1 resulting from the applied force. So this displacement can be obtained using this relationship P is equals to Ku. And then in the previous example, we established that for force P1 and P2 at node 1 and 2, the displacement can be given by, the equation can be given by EA over L, that is the stiffness, negative EA over L, negative EA over L, and EA over L. And then times the nodal displacement U1 and U2. So this displacement we can obtain from this equation. And now the challenge comes when we have a bar like this. We need to get the displacement at any point along the bar. So this becomes challenging because only the finite element in this case obtained. The equation here gets displacement at the nodal points. But there are two ways we can obtain displacement anywhere along the bar. Say we have node 1 and node 2, that is the first approach, and we want to obtain displacement at the middle of this bar here. Then the first approach is we could divide this bar into very many small elements, and with one of the nodes where you want to obtain the displacement being a nodal point for one element, say this. So in this case, if we write this equation for this element, we will have several elements. So we have 1, 2, 3, 4, 5, 6 elements. We will have 6 elements, and we shall assemble the stiffness matrix for these elements. We shall obtain U1, U2, U3, U4, U5, U6, U7. So these are nodal displacement. So our where we need U is U4. So from this we can obtain displacement U4 at the point we want. But this comes with a disadvantage because we shall have a big stiffness matrix which will require a lot of computations and will take a lot of space in the computer. So the best approach that the finite element actually uses, most finite element software uses, is the obtaining an interpolation function. Interpolation function, also known as the shape function or Lagrange function. So this interpolation function works in a way that if we have the element, the bar element, we assume for an axial force P1 and P1 and P2 for node 2 and node 1 respectively, we shall have the displacement varies linearly along the member. So this function, if this displacement U1 here, this node displacement by U2, and then the displacement is given by U is equal to A plus bx, which is the equation of this line. So displacement anywhere on the bar can be given by the equation of this line, u plus bx. Now let's get A and B are unknowns along the line. So let's get the values of A and B by introducing the boundary conditions for this element. So we shall have at node 1 u is equals to u1 and x is equals to 0, because x is the axis along the bar. So at u1 x is 0 and the displacement is u1. So let's substitute back in this equation. This equation u1 now therefore is equals to A plus B times 0, and therefore u1 is equals to A, or A is equals to u1. Now again we apply the boundary condition at node 2 here. So at node 2 of the element u is equals to u2, the displacement at node 2 which is u2, and the x is equals to the length of the bar L. So the overall length of the bar is L, just as we mentioned before in the first diagram. So we substitute again in this equation and say u2 is equals to A now is u1 plus B times x is L. So if we make B the subject here, so B is therefore equals to u2 minus u1 over L. Now we get back and write the general expression for u equals to A plus bx, which is u is equals to u1 plus B is u2 minus u1 over L x. So this is the expression for u, but this therefore means u is equals to u1 minus u1 over L x plus u2 over L x. This is the same as u equals to, let's factor out u. So it's 1 minus x over L u1 plus x over L u2. In matrix form, this can also be written as 1 minus x over L x over L. Now this 1 minus x over L and x over L are known as the shape function. So we can also say this is n1 u1 plus n2 u2, where n1 is the shape function for node 1, which is given by 1 minus x over L, and n2 is the shape function or the interpolation function for node 2, which is given by x over L. So these are the shape function or interpolation functions. This bar element with the two nodes. From here we can get to the concept of strain in order to get the B matrix. So let's assume we have an element, small element with an overall length dx, and this element has been displaced. So we have a new position. This is node 1 prime. Now this is node 1, the new position of node 1, and the node 2 will displace. So, and if this small bar element is displaced from node 1 prime to node 1 and node 2 prime to node 2, then this is a displacement we don't know, extension we don't know, and this also is displaced by u. So this displacement of this point will be given by u, the displacement at node 1, plus du dx, that is the rate of change of displacement along the bar, times the bar length. So this is the displacement here of node 2 prime. Now we define strain as equals to change in length out of original length. So the symbol strain is given by this epsilon equals to the change in length is therefore equals to u plus the displacement of node 2. So the change in length is du dx by dx, which is the extension in of node 2 minus the extension of node 1 out of the original length, which is dx, the small length of the bar considered. So we shall have this will be du dx divided by, because this and this will cancel, out of dx, and our final answer will be strain is equal to du dx. So the strain is equal to du dx. Now in our previous derivation, which is this, u is given by this equation. So u is equals to n1 u1 plus n2 u2, that is the shape function. So du dx now will be the dx of n1 u1 plus the dx of n2 u2. We know n1 is equals to 1 minus x over l, 1 minus x over l, and n2 is x over n. So du dx will be the dx of 1 minus x over l u1 plus the dx of x over l u2. So du dx equals to negative 1 over l u1 plus 1 over l u2. Therefore the strain is given by negative 1 over l u1 plus 1 over l u2. This is the same as negative 1 over l in a matrix form, u1 u2. So which is the same as b u2, where B is the strain displacement matrix. It's not U2, so it is BU, strain displacement matrix, or the B matrix. And the B matrix is negative 1 over n, 1 over n. Thank you for watching.